Yo, welcome back. All right, we are going to look at limits of piecewise functions. So first off, hopefully we remember all a piecewise function is a function made up of different pieces, right? So if I kind of take a look at this function here, f of x, there are two pieces in this particular function. The top piece, x squared minus 5, it's a polynomial, but the way it works is you only use this, you only plug into this if your input is less than or equal to 3, because if your input is greater than 3, then you're going to get the output by plugging into that radical function. Okay, so that's how piecewise functions work. That's the the short of it, the quick part of it. But let's just get to the limits now. So it says use this function to evaluate the following limits. So let's do the limit of f of x as x goes to -1. So how do you do it? Well, here's the deal. If you have a piecewise function and you're doing a limit, right, and you want to do the limit of f of x as x goes to -1, you have to ask yourself, which one of these pieces would allow me to approach -1 from both sides? So in other words, would allow x to get closer to -1 from both sides, or maybe even more specifically, would allow the inputs, the things that I'm plugging in, to get closer to -1 from both sides. Hopefully you're saying the top, because here this is everything, every input that's less than or equal to 3. So there's lots of values that are close to -1 that are less than or equal to 3, right? And so that's the idea. So I would plug into the top. So if I did that, I'd get -1 squared, -1 squared minus 5. 1 minus 5 is -4. That's my answer. All right, let's do another one. All right, it's a pretty cheesy one. Notice the key here. I probably should have had you write that down, but I wrote it down for you. The key is to use the piece that allows x to approach -1 from both sides. So now let's do the limit of f of x, x goes to 5. So, all right, when your inputs, how can I get my inputs to get driven to 5? Which piece would allow me to do that? Well, it would have to be when my inputs are, in this case, greater than 3, because 5 is greater than 3, right? It would be in that interval. And so then I can just directly substitute into that and get radical 5 plus 13, which is the square root of 18. If I wanted to get bananas and simplify that radical 9 times radical 2 is radical 18, right? Why did I do that? Well, because the square root of 9 is simply 3, so I can clean it up and write 3 radical 2. All right, again, use the piece that allows you to approach, in this case, 5 from both sides. All right, so let's see this graphically. So maybe it gets driven home a little bit more. All right, so we'll use decimals like we always do to go ahead and take a look at this graph. All right, so here we go. So here's the first piece that I graphed, all right, x squared minus 5. But notice I only graphed it for x values less than or equal to 3, because that's what the piece was. It's only that parabola when your inputs are less than or equal to 3. Okay, decimals allows you to do that with that little set notation. Then I go ahead and I graph the second piece, right, which is that radical function. But once again, okay, it's only graphed for x values greater than 3. So now think about the two limits that we did. The first limit was as x went to -1. Right, so -1 is right over here. So as my x values, let's see if I can hook up my pen here. All right, as my x values get closer, there we go. Okay, closer and closer and closer to -1 from the left, what are my corresponding functional values getting close to? Well, it looks like that y value. But remember, it's not just about coming in from one side. You got to come from the other side. So as my x values get closer and closer and closer to -1 from the right, what are the corresponding functional values getting close to? And hopefully you're saying -4. And that's what we got. That's what those little limit buggies would be tracking. So hopefully now it makes sense to you why you're only plugging into this piece, this x squared minus 5 piece, right? When you did the limit with direct substitution, you didn't plug it into the radical piece because it wouldn't make sense, because 3 is right here, and to the left of 3, we're defined by that parabola, all right? So now the next question was, all right, well, what's the limit of f of x as x goes to 5? Well, 5 is over here. That's greater than 3. And this function says that when your inputs are greater than 3, use this radical. So here we have this radical x plus 13 graph, right? All right, so now let's take a look. As x goes to 5 from the right, it looks like my functional values are going to that y value. And as x goes to 5 from the left, my corresponding functional values are going to that y value. It looks like it's a little bit more than 4. And take a wild guess at what that is, right? You guessed it. That's 3 radical 2. Okay, that guy right there. So that kind of makes sense that, all right, I get it. Uh, you know, you only have to, you have to choose the right one. So now, not really a great question, to be honest. Those are cheesy questions. I like this question better, which is the next question in the notes, which is, all right, and I'll write it right on here. What's the limit of f of x as x goes to 3? That's an awesome question. Why is that an awesome question? Well, because 3 is right here. So you're like, oh, so what do I plug into? Do I plug in the parabola because I see the or equal to, or do I plug into the radical, right? So a lot of people might say, well, the or equal to, right? So go ahead and plug into that. But you have to remember, man, I hope this gets driven home, that the functional value doesn't necessarily have anything to do with the limit. Remember, the limit is all about what you're approaching when you're coming in from both sides. Also, remember that the question I told you to ask yourself when you're doing the limit of a piecewise function is this. All right, I want the limit of fx, x goes to 3. Which piece allows me to approach 3 from both sides? The answer to that question would be neither, right? Because the blue piece only allows you to come from the right and the red only allows you to come from the left. So hopefully that's telling you that, oh, all right, well, if that's the case, then I'm going to have to do both, right? So in other words, I'll do it right here. I'm going to want to write down and do the limit of f of x as x goes to 3 strictly from the right. And then I'm going to want to do the limit of f of x as x goes to 3 strictly from the left. So now watch again what I ask myself. Which piece allows me to approach 3 strictly from the right? Well, clearly it's this blue piece. Well, that's the radical piece right there. All right. So strictly coming in from the right, I can use that. I'm just going to substitute into that. So radical 3 plus 13. So that's going to be the square root of 16, which is nice. That's just 4. Okay. Now, to do the limit of f of x goes to 3 strictly from the left, which piece allows me to approach 3 strictly from the left? Well, again, you can see I'd be tracking on the parabola. So that's the parabola piece. So I'm going to directly substitute into that. So 3 squared minus 5. 9 minus 5 is 4. Oh, look at that. So since they're approaching the same value, since the limit from the right is in fact equal to the limit from the left, then and only then can I come up here and say, okay, then the two-sided limit is going to be 4. Okay? If these would have been different values, well, guess what? I would have to say does not exist here. But they were the same value. All right? So that's a good thing. All right, so not too bad. So let's keep going with this. There's a couple of little twists and turns, but nothing too crazy, nothing we can't handle. All right, so those are the notes for all of that. So let's get to this guy now. All right, so I want to do the limit of h of x as h goes to 0, right? So now this one, I went straight to it. I didn't give you the 2 cheese ball questions. I'm saying, hey, what's the limit of h of x as x goes to 0? What do you ask yourself? Okay, which piece allows me to approach 0 from both sides? Your answer? Neither. Why? This function is split at 0. To the left of 0, including 0, but to the left of 0, we're a parabola, and to the right of 0, we're a line. And remember, you're like, what about the or equal to? That is what the functional value, if you wanted to figure out what the functional value was there, that's when you look at the or equal to. That doesn't necessarily have anything to do with the limit. So right off the get-go, you would be like, all right, I have to, on my own, do the limit of h of x as x goes to 0 strictly from the right, do the limit of h of x as x goes to 0 strictly from the left. So now I say, okay, which piece allows me to approach 0 strictly from the right? Well, right here, x greater than 0, that's to the right of 0. So I would directly substitute that value, which is 0 in this case, this 0, and I end up getting 1. Which piece allows me to approach 0 strictly from the left? Will that be less than 0? So that would be 5 minus 0 squared. Well, that's going to be 5. And you're like, whoa, wait a minute. Limit from the right is 1. Limit from the left is 5. Therefore, three little dots there, the limit of h of x as x goes to 0 does not exist. Okay? And again, if you're thinking about what's this equal to all about, if I was to ask what is h of 0, so not the limit, but what is h of 0? What's the functional value at 0? that's when I would go ahead and just plug 0 in there. So I end up getting, just so happens it ends up being 5. The functional value is 5 at 0. Okay. All right. So again, let's take a look at the graph of this guy. Nope. You know what? Keep that up. Here we go. So close these off and go ahead and graph. There's my parabola. There's my line. I know it's a little messy because I have that. I'll kind of get rid of that for a second, right? So as I go to 0 from the right, what's going on? It looks like I'm approaching 1, like we got before. When I go to 0 from the left, looks like I'm approaching 5. Now, what Desmos doesn't emphasize, which kind of stinks, is there a functional value there? So I kind of have to do that. And it's plotting that point at 1 there. And up here, it's doing that as well. But that is not correct, right? So really, this should not be oh, there it is. You saw it? You saw it. I almost had it. Someone saw the hole. Go rewind and pause it. There's supposed to be a hole there, right? This is not a dot. There's a hole. Why? Well, because the line says only x greater than 0. All right, hopefully you saw that hole. I saw it. I saw it for it. There it is. There's the hole. That's what the graph is supposed to look like. Okay? All right, so not too bad, not too bad. Let's close that out. Let's come back over here and let's throw ourselves a little curveball. All right, so take a look at this. It's another piecewise function, so that's nothing fancy schmancy. But now the manner in which I define the piecewise function is different than the previous two problems. The previous two problems, one piece was x less than, the other piece was x greater than. So basically the graph was split at some value, and to the left it was something, and to the right was something. That's not what's happening here. Think about what this says. This says, all right, g of x, it's going to be 1 minus x cubed. So it's going to be a polynomial of degree 3 only when x is not equal to 1. So as long as x is not equal to 1, everything around 1, not equal to 1, and everywhere else, you're going to go ahead and you're going to graph this polynomial of degree 3. At 1, specifically at x equals 1, you're this line. But that's kind of weird because you can't really be a line at a point. So if you think about it, this is just going to be a point here. When x is 1, the output would be 2 times 1. It'd be 2. So this is a weird way of saying the 0.12 is on the graph. Okay? And so now what's the deal? If I want to do the limit of g of x as x goes to 1, which one of these pieces am I using? All right? Pause the video. See if you can answer that. Quick little pause. All right? Welcome back. All right, so what did you pick? If you pick the bottom piece, you're still not getting the whole limit deal, right? You probably picked the bottom piece if you picked it because you saw it equal to. But remember, the limit has nothing to do with what's equal to. That's nothing necessarily to do with the functional value at some value. You care about what's going on around 1, not what's going on exactly at 1, because they're not always the same thing, right? Limit is what you approach, not necessarily what you have. So believe it or not, if I'm going to directly substitute this, I can do it, and I can do it in one shot because I could just plug into the top piece. So if I want the limit of g of x as x goes to 1, again, the question is always the same with piecewise functions. Which piece allows me to approach 1 from both sides? Well, this is saying everything around 1 right here. X not equal to 1. Well, that's the 1 then. So then I'm going to go 1 minus 1 cubed, and I get 0. And that is my answer. And I don't have to do a limit from the right and the left the way this is defined. All right, so now let's look at the graph of this. Now, Desmos kind of, I had to get a little fancy with the what's it called? The symbols here. So don't get too hung up on how I did it. So there is my 1 minus x cubed for x not equal to 1. Now, again, they don't draw it for me. So if I actually went right, you saw it there. Where is it, baby? There's got to be an easier way to do this. Oh, there it is, right? That's the graph. It's basically the polynomial of degree 3 everywhere but 1. All right. On top of that, there's that other part, which I said eventually just produced that whole that line. I can't speak. That 0.12. So there's your graph right there. So now think about it. As my x values approach 1, the x value of 1 from the left and from the right, those little buggies tracking on that black curve, what are they tracking towards? They're tracking towards 0. They're not tracking towards 2, right? So the answer would be 0. All right. Hopefully, you guys are replicating these graphs on your notes. Hand draw them. You can use technology as an aid, but for now, I want you to hand draw them. All right, we're getting there. We're getting there. We're getting there. All right, let's take a look at 3 now. 3, similar deal, right? Piecewise function. Looks like I have a rational function for the top piece, and it's the same type of thing, right? We're going to say, listen, we want you to be this whenever x isn't equal to -2. Now, that's actually a good thing because -2 would make that undefined. And then we're saying we want you to be this, k. So k is going to be some number when x is equal to -2, right? And it says find the value of k such that the limit of f of x as x goes to -2 equals f of -2. So whoop, you're like, wait a minute, you just upped the game. You're not just asking me a limit question now, right? You're asking me to find a value of k such that what? Right? So let's think about this. Let's break this down. Say you have no clue what this means or how to interpret it. You do see this, right? There's a limit there. And we just did a bunch of problems where we calculated limits like that. So let's make this our effort. Let's do the limit of f of x as x goes to -2. So let me ask you something. Which one of these pieces allows x to approach -2 from both sides? Hopefully you're saying the top piece, because this is where x is defined everywhere around -2. So it's going to allow you to approach -2, right? So you're like, all right, so then that means I want to do the limit. Oh, what's going on, Pen? Pen's freaking out. Let's try it again. Let's maybe switch it up to red. Maybe it likes red. There we go. Let's do the limit of, and instead of f of x, I'm going to write the piece that I want to use. I want to do the limit of x squared minus 4 over x plus 2 as x goes to -2. So, all right, let's do that limit. You learned this the other day, right? First thing you try in a limit problem is direct substitution. Chuck -2 in here. -2 squared is 4, minus 4 is 0. -2 plus 2 is 0. Oh, look at that. Look at this spiral review. What is that? That, my friends, is an indeterminate form, which means we don't know what's going on, so we have to try something. And this is one of the very first things we tried when we did this, right? What can you do to the numerator? Hopefully you're screaming, factor, factor. So you can factor this into x plus 2, x minus 2. Why would I do that? Well, because now these x plus 2 factors cross out, and now I can resubstitute, right? So I can go ahead and chuck -2 in. I'm going to be a little lazy and not rewrite and just chuck -2 in this simplified expression. -2 minus 2, -4. So I get that this limit is -4. So now you're like, all right, well, what is f of -2? That's a functional value. So if I want to find the functional value at -2, right, what do I have to do? I have to say, look right here, because this is what's going on at -2, and my output is just that. It's k. So I get k. So then I end up getting that -4 equals k. So that's me finding a value of k such that it's equal to this limit, right? Such that f of -2 is actually equal to the limit of f of x as x goes to -2, right? It ends up being -4. If this would have been like 2k plus 1, I would have set the 2k plus 1 equal to -4, and I would have solved it for k. Now, it's actually kind of neat because we're kind of setting you up for a better question, and it's going to be tough to do in Desmos because they don't graph those holes for me. But let's go ahead and graph this thing. All right, so I might mess with this graph a little bit. So there is that first part, which quite honestly should make sense to you that it looks like a line. All right, and maybe I'll actually show the work for this. All right, so let me come over here and kind of re-show you what we just did. So think about what we just did. When we were doing that limit and we had x squared minus 4 over x plus 2, we factored the top. And when we factored the top, it was x plus 2, x minus 2. The x plus 2's canceled. You end up getting this. Now remember, there's more to the story than just saying these are equal, right? Because in this expression, x is not allowed to equal -2, which means it can't equal -2 in that expression, because this is the mama dog. This is what I'm simplifying. So if I was to do this, I kind of have to write, all right, this is true as long as x isn't equal to -2, because it would cause that to be 0. So, all right, what does that mean? Well, let me go ahead and take a look. Actually, no, we don't. We can see it right here. All right. If I look at x minus 2, this is a line, slope of 1, y-intercept of 2. What's going on at negative 2? Well, once again, if I do that, bam, right, there's a hole there because x isn't allowed to equal negative 2 because the expression is actually x squared minus 4 over x plus 2. So we have that going on. So then you have this negative 2k business, which is just a point. And depending on what k is, depends on what the point is. So see how I'm sliding the k value? There's a k value of 5, there's a k value of 10, there's a k value of 8, there's a k value of, negative 1.9. So this can be any k value that we want. Now the question says, right, if I go back to it, says find a value of k such that the functional value at negative 2 actually equals the limiting value. So if I go back here, think about what we're doing. And let me just sketch in that hole so I don't have to play the game of holding the button down, right? If I sketch in the hole that belongs here, negative 2, there's supposed to be a hole right there, right? And that's the y value of negative 4. So now there's a hole there. So now I want to find a value of k such that the functional value is equal to the limit. Well, guess what I have to do? I have to fill in the hole, right? So when k is equal to negative 4, it fills it in. So now, why did I say before we're setting you up for a better question? Because the question in the future is going to be this. Find me a value of k that makes the function continuous. And you're going to have to know that that basically means fill in the hole. More specifically, you're going to have to know that that means when you do the two-sided limit, right? So when you go ahead and do the two-sided limit of f of x, as in this case, x goes to negative 2, that's the two-sided limit as x goes to negative 2, you're going to have to find the k value that makes that equal to the functional value, that fills in the hole, so to speak. This is a fancy way of saying find the k value that fills in the hole, right? More to come on that when we specifically discuss continuity. We're not there just yet. All right, last question. All right, this guy, you're ready? So we have a piecewise function. All right, looks like we're giving you lots of parabolas and lines. And now again, we're back to this is one of those ones where there's a split situation going on, less than, greater than, right? So when the inputs are to the left of 0, we're going to be this parabola. And when the inputs are greater than 0, we're going to be this line. And it says find a value of k such that this happens. The limit of f of t as t goes to 0 is in fact equal to f of 0. Then you can see Mrs. Haas here put a nice little note, aka you're basically finding a value of k that makes the function continuous. All right. So, all right, let's rock and roll. So let's try and do it without the graph, and then we'll use the graph as just like a fortification, if that makes any sense. So again, you're like, I don't know. What do I do? Well, just take a look at this limit right here, right? You know how to do limits. So let's do the left side of this equal sign. How do I do the limit of f of t as t goes to 0? Well, I ask myself, which piece allows me to approach 0 from both sides? You should be saying neither, because I'm split at 0, right? So that means that you on your own would have to do the limit of f of t as t goes to 0 from the right, and then you'd have to do the limit of f of t as t goes to 0 from the left. So which one allows me to approach t? Which one allows t to approach 0 from the right? That's going to be that guy. So that's 2/3 0 plus k, which is just k. Okay. Which one allows t to approach 0 from the left? Well, that's going to be that guy. That's 3 minus 0 squared. So I get 3. So now think about this, right? In order for this equation to be true for some value of k, this limit must exist. The only way this limit can exist is if the limit from the right equals the limit from the left, right? So then that would mean that k would have to equal 3. Because if k equals 3, then the limit's going to be 3. And then you technically should check, well, what the heck is f of 0, right? And it seems weird that we check f of 0 because you look to do the functional value, you look for the or equal to now. It's the only time you look for it. So you're saying, all right, that tells me to plug into here. So I get 3 minus 0 squared. So I get 3. So, okay, the limit was 3. The functional value is 3. And you're kind of saying, well, didn't you kind of do that when you did this? And the answer is, yeah, I did. But I could have had a piecewise function where there was a third piece, and maybe it did something like that, t equals 0. So it is necessary to check that, even though it seems redundant when you have a or equal to 0 on one of the pieces. Okay. All right, real quick, let's just take a look at the graph and see what the heck's going on with this. All right, so if I looked at the graph now of this guy, oh, did I not put this one up? I didn't put this one up. I thought I did. All right. Well, you know what? Leave it up to you guys. You guys can graph it. Graph that bad boy right here. Use Desmos, use your TI-84, use GeoGebra, graph it appropriately, and see if the answer that we just came up with actually makes sense. Okay. And I'll leave that up to you. And if it doesn't make sense, guess what you do? You ask me a question on Wednesday during our live sessions. All right. Be good.